All right, back of the second page, and here we have some content. I know you guys might not necessarily be able to read the smaller print, but you should have your copy of your packet with you. Percent error is the accepted value minus the experimental value, and that's an absolute value. If you notice the absolute value signs, that means it really doesn't matter which way you do this, but you're going to treat this as a positive value, divided by the accepted value times 100%. And so for our first thing, it says in an experiment you calculate the density of aluminum block to be 2.72 grams per cubic centimeter. The density of aluminum is actually 2.70 grams per cubic centimeter. So calculate the percent error. I'm going to do my accepted minus my experimental, but I'm taking the absolute value. I'm going to divide that by my accepted times 100. And so I'm going to use a calculator. I'm going to get my calculator out and do 2.7 minus 2.72, and that gives me negative 0.02, but I'm going to take the absolute value of that, so that gives me negative 0.02 over 2.7 . So I divide by 2.70, and then I multiply it by 100. I have a percent error of 0.7407, blah, blah, blah. But let's check. We have 1, 2, 3 sig figs here, 1, 2, 3 sig figs here. I'm going to give my percent error to 3 sig figs too. So there I go, 0.741% error. Okay, percent yield, and I know sometimes I've discussed this differently, but this is what I got out of it divided by what I should have got out of it. So this is the best way to calculate it. So for this example, it says in an experiment, I obtained 0.650 grams of Cu. The theoretical yield would be 0.745 grams. So what's my percent yield? Well, I got 0.650 grams, and I thought I should have gotten 7.45 grams. So I'm now going to grab my calculator, 0.65 divided by 0.745 times 100. I only got 87.24%. Well, let's see, there's 3 sig figs, there's 3 sig figs, so I'm going to go with 87.2%. And we could account for some of that. Maybe we spilled something, maybe we did something else, maybe I calculated this wrong, because frequently this theoretical yield comes from stoichiometry, which is unit 6. Okay? All right, this area is for you to write out the rules for sig figs in your own words. I'm going to leave that for you to do, but I'm going to give you some examples right now that you can hopefully follow along with. So I'm going to add 2.3 plus 3.25 plus 5. And my rule for that is the limiting value is the biggest place value. My biggest place value, he is a ones place. So I'm going to give my answer to a ones place. So when I do 2.3 plus 3.25 plus 5, I get 10.55, but I'm going to say the answer to that is just to the ones place, or 11. I do the same thing with subtraction. Now this one's a little tricky because this 100 has 1 sig fig and it is in the 100s place. So my answer is going to be in the 100s place. If I do 467 minus 100 minus 3.2, I get an answer of 363.8, but in the right number of sig figs, I should really say that's still really close to 400. I'm going to round up. Now, remember I've told you if you want to go 1 sig fig more, that is okay. So you could say 360, just like with this. If you wanted to go 1 sig fig more, you could have said 10.6. 1 sig fig more is usually okay. So when we multiply, now we're just going to go straight based on numbers of sig figs. This has 2, 23 is 2. 1, 2, 3. For 35.4, that's 3. And 12.001, remember these O's, the zeros count when they're sandwiched between other numbers, so that's actually 5. Well, my limiting is 2. So I should give me 2 sig figs.
Good afternoon, Brentsville. It's time for your afternoon announcement.